just sort of as a reminder of the stuff that we did last time. So we started chapter 6 with this, which is this thing about thermochemistry, basically the energy in chemical processes, chemical reactions. So we had a bunch of definitions, right? Energy, the law of conservation of energy, which is the same as the first law of thermodynamics, potential, kinetic energy, temperature, heat, work, all of these things that go into the language of what we're talking about. And energy is important in chemistry because when we look at chemical reactions occur because they're striving to get to the lowest energy state, or the most stable state overall in most cases. And so we looked at and talked about the internal energy of a system, where the system is that thing that we're interested in. And so just as we go back up here, right, the system, which you have in here, I'm using the wrong, gotta get back to my pen. There we go. Okay. So if we think about, that didn't work, the system, right? The system here, right, is the thing that we're interested in, okay? Whereas if you think about the surroundings, it's everything else. And so the universe is composed of the system and the surroundings. And so the energy of the universe is going to equal the energy of a system plus the energy of the surroundings. But we're often interested in these changes in energies. And so when we think about a change in energy of a system, it's the final energy minus the initial energy, and for the system itself. We could also look briefly at work. We're not going to spend a lot of time at work or at work with work, the idea of work as an energy relationship in here. We've also looked a little bit at calorimetry. Now, so we looked at with calorimetry, which is the science of measuring heat, right? You need this device, this calorimeter, and in particular, we're going to be interested in the coffee cup calorimeters, and we're going to, bomb calorimeters can be a little bit more complex. And so like we wouldn't even be looking at a bomb calorimeter in lab, but we would be looking at a calorimeter. So something I actually want to do here, actually add a slide in here because there's something I didn't touch on yesterday that I wanted to touch on today. Okay, and that's the idea of sort of system surroundings and the universe, okay? So when we do calorimetry, okay, our calorimeter is kind of like a little universe in and of itself, okay? Now we use the heat capacity of the water in order to measure the energy change of either a reaction or a transfer of energy from an object. So a little bit more on that as we get into an example of it. But before we do that, the thing that I want us to think about is the idea of the energy of the universe, and how the energy of the universe is going to just be the sum of the energy of the system that we're interested in. Okay, and in the future, I'll just abbreviate that as SYS, okay, plus the energy of the surroundings. And I'll abbreviate that in the future, SURR, okay? So when we think about all of the energy out there, it's the thing that we're interested in, right? Plus the energy of everything else, right? And so when we look at the energy of the universe, and we know that the change in energy of the universe is 0, right? That's coming from the law of conservation of energy. Well, we can think about the changes in energy of the system and surroundings and how that relates. So we can say delta E of the universe. So the change in energy of the universe, which we know is related to the change in energy of a system, right? Just because that's how the universe is defined, plus the change in energy of the surroundings. Oops, need my delta in there. We know that's equal to 0 because of the law of conservation of energy. Well, then what we can essentially do here is, as we look at the energy of a system, right, this delta E of a system is going to be equal in magnitude but opposite in sign to the change in energy of the surroundings, okay? And so when we have our coffee cup calorimeter, right, we got this calorimeter, Inside the calorimeter, we got some water, right? We got a thermometer in here, right, with its little tick marks to measure the temperature. And then we've got some sort of a chemical reaction that occurs in here, right? Right, and then we've got our water. Well, we can think about the calorimeter, right, is kind of the equivalent to this little universe, okay? It's kind of a universe in that it's insulated from its surroundings, right? So when we think about it as being this little universe, we can now think how since it's insulated from everything outside of it, we can now think of the chemical reaction or process that's occurring, right, as being our system, and the water, right, as being the surroundings. Okay, and so what we can do is what we're really measuring is we're measuring the temperature of the water. Right, so you can get the temperature change of the water. We also, you'll see as we get into our next slide, we'll see we know some things about water to help us as we measure chemical reactions and the energy that changes in a given chemical reaction or a process. So a process can be something like melting or freezing, right? That's a process, or maybe just the transfer of energy from one thing to another. Okay. So how do we use calorimetry to measure heat? Well, yeah, Amir, you have a question?
Yes, sir. You said delta E universe is equal to 0. Is that a law or
Yes.
something
So that
just in this case?
yeah, if we go back to delta E of the universe equals to 0. So if we look at the law of conservation of energy, right, energy can be converted from one form to another, but can be neither created nor destroyed. So when we think about it being converted from one form to another, this piece here, right, or moved, for example, right, that can be, we're talking in that case, like heat versus work. But the idea of it not being created or destroyed, right, that's the total energy of everything, right? That's the energy of everything. Actually, and that's part of this next one, right? The first law of thermodynamics says the energy of the universe is constant. And these two things are essentially the same. They're just kind of worded in a little bit of a different way, right? So you can convert energy from one place to another or one way to another, but overall, all of the energy that's out there stays the same. So the delta E of that universe is going to be 0.
So as long as we have some sort of isolation for any sort of system, the energy inside basically is not going to be changed.
Yeah, so with that coffee cup calorimeter, one of the things we talked about in that coffee cup calorimeter is how, well, the reason we use the coffee cup in particular is it's a really good insulator, right? So it essentially stops the heat from going in or out of the system. And so if the heat doesn't go in and out of the system, or energy doesn't go in and out of the system, then essentially you have this little universe, if you will, a model universe, you know, in and of itself within that insulated container.
Thank you very much.
So the way we can use this now is, well, first off, we know some things about heat capacities of various substances. So you can see we have some materials here that have heat capacities. And for water as a liquid, we've got its specific heat capacity and its molar heat capacity. Really, if you just multiply the specific heat capacity by the molar mass, right? Or excuse me, multiply by the molar mass. Make sure I got that right in my head. Grams per mole. Yeah. Yes, you get the molar heat capacity there, right? And so if you look at this, right, water has 18 grams per mole. So if you multiply 4.184 by 18, right, you should get this value of 75. Okay. And so we've got, though, something else here that's important is if you notice, we have to take into account the state of these substances. So if you think about why, or what phase something is in, the proximity of the molecules to each other and how they interact with each other will have something to do with why there's a difference between the different amounts of energy. Remember, the heat capacity is the amount of energy it takes to raise the temperature of a substance, or 1 gram of a substance, by a degree Celsius. So if we think about the proximity of the particles and how they're laid out for something like water, well, the solid, right, those solid particles are locked in place. So as you add energy to it, those particles just vibrate more. So it doesn't take a whole lot of energy to get them to vibrate more. When you look at a liquid, those particles are moving around with respect to each other. So the water molecules may move next to other water molecules. When that happens, those attractive forces between the particles, which we're going to explore those attractive forces more in depth in chapter 10, but there are these attractive forces which we know of from sort of the end of chapter 5 in van der Waals equation. We had to take into account these attractive forces. So as these particles move away from each other, you have to break them apart. You have to pull apart the molecules, which takes energy because there's an attraction between those particles. So it's going to take more to cause those water molecules to move away from each other in the liquid phase, because you're essentially having to break some of these attractive forces in order for them to move. So it takes more energy to raise the temperature of liquid water than it does to raise the temperature of solid water, because it's a difference between causing more vibrations between neighboring particles versus letting those particles move around with respect to each other. Now, when you have a gas, what we know about gases is they're very far apart for the most part. And so those attractive forces between the particles are very, very, very small. And so it takes very little energy to raise the temperature of a gas also, because you're not worried about the attractive forces between particles. You're just worried about getting those particles to move faster. Okay, so the phase of a substance does matter here. And so that's why you have differences for the liquid, where the liquid water has a specific heat that's about double that of solid water and of water in the gas phase. Okay, now something like water, right? Water has a specific heat because of its phase, but you'll notice that when we look at other substances, like say iron, right, or aluminum, or lead, or mercury, right? All of these other substances that we have here, they're all solids. Jessica, I'll get to your question in a second. But those solids, when you look at something like a solid metal, right, those are going to have very small heat capacities. It's not going to take a lot of energy to raise the temperature of a metal. They conduct energy very, very well. And we're also talking about particles that aren't moving with each other. So you're just exciting more vibrations in between particles, essentially, when you add more heat. Whereas with water, you're really worried about these other forces, these intermolecular forces that we'll dive more into in chapter 10. Jessica.
So these heat capacities that you have written down for like water, iron, aluminum, will that be given, or is that something we need to memorize?
It could be given. You don't have to memorize it. Yes, it could be given, or it could have you calculate something. Okay. I don't expect you to memorize anything. What I would say is it would be useful for you to know this one, right? This is the specific heat capacity of water in its liquid form. That's a very common one for us to know.
Okay, thank you.
Mm-hmm. So we can see how this gets used doing a bit of an example. Okay, so our example, what will be the final temperature if a 100 gram piece of iron metal at 100 degrees is placed into water, 50 grams of water at 20 degrees. And so here, what we can look at is essentially the process that's occurring here, right? Is the iron, okay, so as we think through this, right, the iron, when you put hot iron into the water, it's going to transfer some energy to the water. So iron is going to give energy to water, and it'll do so because there's a temperature difference, right? So if there's a temperature difference and the energy is transferred because of a temperature difference, it's going to transfer that energy as heat. Okay? And so that's kind of the first thing as we look at this type of a question. What's going on here? Well, we're going to have iron is going to give off some of its energy. It's at a higher temperature. It's going to strive to get to a lower temperature as the temperature of water goes up, and they're going to wind up at the same temperature. That's one of the key things of calorimetry is at the end of an experiment in calorimetry, everything inside of that coffee cup or whatever insulated container you have is going to wind up at the same temperature. And so thinking about that and the amount of heat that's transferred from, say, the iron to the water is going to be related to the specific heat, okay? And so that's where we have the two keys here, right? The first thing is we know, since this is in an insulated system, right, and we're saying we have this little universe, the heat of the water is plus the heat of the iron, right? The heat of the water, right? Energy is going up, so that'll be a positive value for the water, but for the iron, the energy is going to go down because it's giving off its energy to the water. And so those heats, right? Remember, and we're thinking about heat and energy being essentially equivalent here because this is constant pressure calorimetry. So we're not going to deal with the pressure or with the work at all because our volume of our liquid is going to stay the same. So what that means is, and you can kind of see here, right? If we take our specific heat, we see, okay, well, the specific heat is the specific heat capacity, rather, is the heat required to raise the temperature of 1 gram of a substance by a change in temperature per degree Celsius. So we can rearrange that equation. When we rearrange this equation, we get Q is equal to MC delta T, right? Q is equal to MC delta T. And we know that our delta T, remember delta T is equal to T final minus T initial, okay? And so the other thing we can do here is we can take that equation where we have Q of water, the heat of associated or that water gains, plus the heat that iron, or the heat change of the iron, right? The amount of heat essentially that the iron loses, lost my E there, right? And we can rearrange that and we can say, well, the Q for water will equal negative Q for iron, okay? And we can use that, and really the reason for that is that if you think about the delta T for water, water is absorbing that energy, so its temperature is going to go up, whereas iron is giving off its energy, its temperature is going to be, or temperature change is going to be negative, and so that negative sign essentially allows us to take that into account. So let's take what we know there, okay? We've got Q for water and Q for iron, and what we can do to add to this is we can say, well, okay, if Q is equal to MC delta T, we can say, well, we have the mass of water times the specific heat of water, and I'm going to specifically say H2O liquid there, times the change in temperature of water. So I'm going to say T final minus T initial for water, and that will equal the mass of the iron times the specific heat. Oops, that's the wrong one. Come on. Okay, times the C sub S, not S. Right, so times the specific heat of iron times the delta T of iron, which is T final minus T initial, right, for the iron. But the other thing that we can do here is essentially see what two things are the same. So in this case, the final temperature of the water and the final temperature of the iron, right? Those two things are going to be the same. Because it's all in the same insulated container. Yes, Maya.
Is the temperature of water increasing because iron is decreasing, correct?
So that a better way to put it is, as the temperature of iron decreases, the temperature of the water increases because the iron is giving off energy to the water.
Now, the next question is there always going to be one going up and one going down, you know, in terms of temperature? If we're
Yeah, because when one thing gives off energy and another thing absorbs it, right, the heat that of one of them is going to decrease, the heat of the other one increases, and that can be measured, right? Heat is measured by the change in temperature. Yeah, so as the temperature of one goes up, the temperature of the other will necessarily go down.
Cool, thank you.
Let me clarify something else though. That's for a process like this where you have a piece of iron, say, that you're putting into a solution. If you were to have a chemical reaction that takes place in a solution, like let's say you had an acid and a base, and you mix so the solutions, a 1 molar acid and 1 molar base, and you mix those together, assuming they were initially at the same temperature. Let's say you had 50 milliliters of 1 molar acid and 50 milliliters of 1 molar base, and you mix them together. As soon as you mix them together, you now have 100 milliliters. All of that water will increase in temperature as the acid and base react. Now, the reaction between the acid and the base is going to give off energy that raises the temperature of everything there, right? So in a sense, we have to think about that reaction as producing the energy, as opposed to with the iron and water, where the iron gives off the energy to raise the temperature of the water, right? So the energy to raise the temperature has to come from somewhere in the raising the temperature of the water. In the case of the iron, it's the iron cooling down, giving off energy. In the case of a chemical reaction, it's the bonds that are being formed and broken that causes that heat to come. So in that sense, the thing that you're measuring the temperature of, that water in a chemical reaction, the water's temperature is going to go up. You're not going to actually be measuring the temperature of anything that's going down, because it's if you will, the energy of the thing that's going down in a chemical reaction is the reactants going to form products. We're going from reactants are higher in energy to form products that are lower in energy, causing a water temperature to go up. So that's something we'll explore a little bit more and talk a little bit more about when we look at sort of exothermic versus endothermic as well. So sort of the process does matter here too, right? Okay, so we're going to take these values and we're going to plug them in, plug all the values in that we need to. Oh, I got two hands raised. So hold on a moment.
Mine is regarding a new question.
Okay, go ahead, Amir.
On your last slide, the one that you were doing, yeah, thank you. The energy of the iron, I believe that you need to also multiply it by a negative
Yep,
on the very last part.
Yep, I missed that in there. Thank you. There should be a negative sign, right?
Yep.
Change my color back. Hold on. Thank you, Amir. And then somebody, was that the other comment also? Probably. Okay, so let's go plug these values in here. So we've got 50 grams of water, 100 grams of iron. The iron's at 100 degrees, the water's at 20 degrees. And then we've got values, as you can see listed at the right here, right? 4.184 for the water because it's in its liquid form. And for the iron, we've got 0.450. So we'll go to our next slide to give us some room. Okay, so for the water, right? So this is going to be Q of water equals negative Q of iron. So here we've got our 50 grams of water times the specific heat of water, 4.184 joules per gram degree Celsius times the delta T. So T final, I'm just going to leave as T final, minus the initial temperature, which is 20 degrees Celsius. Now, if you want to, you can convert it to Kelvin, but since it's a change in temperature, it doesn't matter whether it's Kelvin or Celsius, right? So we're going to say 20.0 degrees Celsius will equal negative the mass of the iron, so 100.0 grams of the iron, times the specific heat of the iron, which is 0.450 joules per gram degree Celsius, times the temperature change. So this is the same final temperature because they're in the same container at the end of the experiment, minus the initial temperature, 100.0 degrees Celsius. And so for this, all you have to do is solve for that final temperature. So we can multiply, for example, the 50 times 4.184 and distribute. So we wind up getting 209.2 units of joules per degree Celsius times T final minus 4,184 joules will equal, and we do the same thing on the other side. So negative 45.0 joules per degree Celsius plus 4,500 joules. Right? And that value actually should have 3 sig figs here, right? So I'll underline that. And then so we just rearrange and you wind up getting, so if you add 45.0 joules to each, joules per degree, oh, I've lost my TF there. There should be a TF right in there. So if we add 45 joules per degree Celsius times TF to the final temperature to each side and add 4,184 joules to each side, we wind up getting a value of, so 254.2 joules per degree C times TF is equal to 8,684 joules. Okay, just math-wise, if we divide each side by 254.2 joules per degree Celsius, right, our joules are going to cancel. Joules per degree Celsius are going to cancel. This degree Celsius is going to flip up into the numerator, and we wind up with a final temperature of 34.2 degrees Celsius. So this is one way that a calorimetry question can be asked. Essentially, what do you expect the final temperature to be? Now, in a calorimetry experiment, because we have this relationship between the heat of transferred from the iron to the heat of the water, we can actually measure, based on the initial and final temperatures, how much heat is transferred also. So that would be a different way to ask a question like this. And so you could say, well, how much, or what is the heat capacity of a substance? Or if you have a chemical reaction that occurs, based on the heat that's absorbed by the water, how much energy is given off by the chemical reaction? And then you can divide that by the moles of chemicals that are reacting to figure out the energy change of that chemical reaction. Right? So that's just a quick calculation for how you would approach a calorimetry experiment. Okay. So in a chemical reaction now, we want to look at Hess's law. And one of the things to bring up with a reaction. So what we're going to do actually is I'm going to take one of these reactions, and I'm actually going to give us a new slide. So I'm going to give us a new slide in here. And we're going to talk a little bit more about enthalpies of reactions here in a sec. On the fly here. Okay. So if we think about a chemical reaction, one of the things we're going to look at here in a second is what's called Hess's law. And Hess's law is a law that deals with multi-step reactions. Now, Hess's law states that the enthalpy change in any reaction is equal to the sum of the enthalpy changes of the steps. So in a chemical reaction, overall, you might have this a very complex chemical reaction that takes place in multiple steps, and you might be able to narrow down those each of those steps and say, well, there's some sort of an enthalpy change associated with that. How much heat is given off in a given chemical reaction? And so before we dive a little bit deeper into this, we're going to go and bring up our first chemical equation here, reaction 1. And so what we're going to do with that, we're going to take this reaction 1, we're going to talk a little bit about it, okay? And so this sulfur solid plus O2 gas goes to form SO2 gas. Okay. So this particular reaction, as you can see from where that arrow there, comes along with a delta H, right? This enthalpy change. And so the enthalpy change for this reaction is negative 296.8. Okay. So delta H equal to negative 296.8 kilojoules. Okay. So when you look at this chemical reaction as written, we're saying 1 mole of sulfur reacts with 1 mole of oxygen to produce 1 mole of sulfur dioxide. When that happens, we get this enthalpy change that is negative. This negative enthalpy change, right, says that energy is given off to the surroundings, okay? So the negative enthalpy change, okay, says that energy goes from the reaction or from the reactants to the surroundings as products are produced. Okay, that is an exothermic reaction. Okay, that's an exothermic reaction there. Now, this chemical reaction, if we think about what it means to be exothermic, right? Exothermic says that essentially heat is a product. So what we're really doing is we're comparing the overall potential energy stored in those initial bonds, well, sulfur and oxygen, compared to that with the sulfur dioxide. And when you have something that is exothermic, it says that the products are lower in energy right, than the reactants, okay? When we say they're lower in energy, this idea of something being lower in energy, right? That's a W for real, okay? So when we think about something being lower in energy, what we're really looking at here is we're saying, okay, so what do we mean by lower in energy? Well, let's think about this from the standpoint of if I have a ball in the side of a cliff, right? You have a ball here. It's going, when it rolls down the cliff and into this ravine, it's going to wind up down here at the bottom. It wants to be at a lower point. It wants to have a lower potential energy. When we think about it being at this lower point down here, that ball, when it rolls down, is going to be at a more stable position. Okay, so we can equate lower in energy to being more stable, okay? So if we have a molecule, if we're comparing two molecules in one, or we're comparing our reactants to products, in this case is the better way to look at it, if our products are lower in energy than our reactants. So we can do that, depict that using an energy diagram, okay, where we have our products. So in this case, sulfur solid plus O2, excuse me, sulfur, yeah, solid plus O2 gas. So the sulfur is burning. Our product, the SO2 gas, will be lower in energy, right? So the reaction that occurs says that the energy change there, so here to here, right? That difference is going to be our delta H, right? And so for delta H less than 0, that's exothermic, right? If instead we had a reaction that produced products that were higher up, that would be an endothermic reaction. And so thinking about the energy that's associated with this will help us to better understand what's going on in a given process, right? We tend to want things to, or we follow things, the energy of a system tends to want to go to a lower position. Now, where is all that energy going? Well, if it's an exothermic reaction, it's going from that system, from those initial reactants to the surroundings as those products are formed, okay? Yeah, Amir.
Products are like always lower in energy than, lower in energy than the reactant, right? Regardless of it being exothermic or endothermic.
No. So remember, we're talking about a system here, okay? So when we think about a system, the system can be exothermic or endothermic. Now, if you have an endothermic reaction, okay, instead of that energy going out to the surroundings, in an endothermic reaction, the energy is going from the surroundings to the system. So remember, energy isn't being created or destroyed here, right? We're just looking at the system itself. So if we consider the universe stays the same. We look at the system. If the system's energy goes up, it has to get that energy from somewhere. That's where the surroundings are providing the energy to drive the reaction. What you'll find is, in Chem 102, when you get into thermodynamics, which is like chapter 17 in Chem 102, thermodynamics, which is related to thermochemistry, they're essentially, thermochemistry is sort of part of the thermodynamics field. But basically what you're looking at as far as whether something will occur spontaneously, the only reactions that will occur spontaneously are going to be governed by something else, which you'll explore more deeply in a Chem 102 class. But no, if we think about a system itself, it can be either exothermic or endothermic, and that just governs where the energy is either coming from or going to in a given reaction.
But a reaction wouldn't happen unless it actually brings basically the products are usually more stable than the reactions, or else it would have gone backwards, isn't it?
In many cases, that's true, but there is something that we are not diving into that you would look at in a thermodynamics course, and that's what's called entropy. Now, entropy is really the dispersion of the energy as a driving force for chemical reactions. So essentially, you're saying if energy goes from a reaction to the surroundings, that increases this other thing, this entropy in the surroundings, and that can be driving a chemical reaction. But you can cause a reaction to go in the opposite direction, right? By putting energy in, by forcing it to go, by either doing work or adding heat to something in order to get it to the reaction to occur. For example, if you think about just simple reactions that would be applicable in today's society as we start to transition into fuel sources that are alternatives to, say, gasoline, you can think about a fuel source like hydrogen gas, right? Hydrogen burns in the presence of oxygen to form water. Okay, so that gives off energy. That is exothermic. Okay, but you can cause water to split to form hydrogen and oxygen, right? Now, it may not be particularly efficient to do that, but you can split that hydrogen and oxygen to split that water to form the hydrogen and oxygen. And that means you would have to put the energy in from somewhere else. Okay, so what you're probably thinking of is the spontaneity of a reaction. and spontaneity of a reaction isn't even fully driven by this heat or the enthalpy change. For example, that hydrogen and oxygen burns, it gives off a lot of energy. It does that spontaneously. But there are spontaneous reactions that are actually endothermic. And an example of that would be if you're familiar with the instant ice packs, right? So the instant ice packs have generally some sort of a substance in a container. Now you have the way this would work is you would have, and out here I'll draw this out on the screen here. So like if you look at an instant ice pack, right? You have essentially a package plastic container, right? That has water in it. And inside that container, you've got some sort of a salt, right? And those things, you're supposed to smash them, right? You break them apart and that salt dissolves, right? As the salt dissolves, right, it absorbs energy, right? But it does so spontaneously. So as the salt dissolves, it pulls energy around from its surroundings. Well, in an instant ice pack, those surroundings happen to be you when you put it on your, let's say, your sprained ankle or sore muscle, right? The heat that is driving or helping to facilitate the solubility of that salt dissolving is coming from an outside source, okay? Does that make sense? That sort of clarified that a little bit?
Yes, thank you very much.
Maya, do you have a question?
Yes, I did. So I'm just trying to understand exothermic. So if energy cannot be destroyed, obviously, is heat technically a product?
Yeah, so that's a way to look at it. So you could almost
like it's like sulfur plus oxygen equals
So you could over here you could go
heat.
and let me change my color so that here we go. So if you wanted to, you could go over here and say plus heat. Absolutely. In fact, that's a really good way of looking at it. Is if you have an exothermic reaction, heat is a product. If you have an endothermic reaction, heat is a reactant. And that's something you'll use a bit more when you start looking at equilibrium in a Chem 102 class as well, because in equilibrium, the amount of heat or the temperature at which a reaction takes place can have an influence on the direction a reaction will go. And so we could write out that same chemical reaction for sulfur dioxide, but in the reverse. For example, you could potentially take SO2 and split it, right? So you could reverse this reaction and form sulfur solid plus oxygen gas. So if that were the case, you would have to change the delta H for that particular reaction, and it would just be the same magnitude but opposite of sign. So that for this reaction over here in blue on the left, you would actually have an enthalpy of that reaction of 296.8 kilojoules. And so that's something we're going to explore a little bit more in a minute, but you could cause that reaction to be reversed. Essentially, you have to force it in the other direction or force it to flip the direction in which it's written. And so in that case, you could think of that heat as being a product, or excuse me, as being a reactant, right? Yeah, so this is something that we can think about.
Yes, cool.
Sort of a little bit is sort of reversibility of reactions. Go ahead.
No, I was just saying thank you. Thank you.
Oh, okay, great. So let's go back to this now, this idea of Hess's law. So Hess's law, we've got basically now we can look at this reaction here as taking place in two steps. Okay, we've got the first step. So the reaction that we're going to look at is 2 sulfur solid plus 3 O2 going to form 2 sulfur trioxides, which this is an example we talked about sort of right at the end of the gas chapter 5. And in that chapter, there are these chemical reactions that we said take place when you burn coal, right? This is part of acid rain, essentially, acid rain chemistry. Now, this takes place based on 2 different potential reactions. The first one you see here, right, that is the one we've looked at a little bit already, right? This where we have the first reaction is negative 296.8 kilojoules for its enthalpy of reaction. But the second step in this reaction, whereby the sulfur dioxide gets converted to sulfur trioxide, right, occurs by this chemical reaction. Now, the thing about this is, when we look at this chemical reactions, we can't just add them together, because when we add them together, we wouldn't get the overall reaction here. But what we can do is say, well, the first reaction can be added to the second reaction in some proportion of the two reactions. And so the first way we're going to look at this is say, okay, well, if I want to get this final reaction seen here, I've got 2 sulfurs plus 3 O2 gives us 2 SO3s. In order to get to that particular reaction from these two, I have to sort of troubleshoot this and figure out, well, how many of these reactions do I need, right? And so one of the ways I can look at it is I can say, well, let's look at the stoichiometric coefficients here, right? There's a 2 in front of the sulfur. Well, I only have a 1 in front of this sulfur. So in order to get 2 sulfurs, and that's the only place that I have sulfur, I have to multiply this equation by 2. So if I do that, I say, okay, well, 2 times reaction 1. So what does that give me? 2 sulfurs plus 2 O2 reacts to form 2 SO2. Okay, that's good. That's a good start, okay? Now, if I do that, if I multiply the reaction by 2, I have to necessarily multiply the enthalpy by 2, because as it's written up here, right, the way that this is written up here says 1 mole of sulfur plus 1 mole of oxygen gas produces 1 mole of sulfur dioxide, right? That accounts for the production or the giving off of these 296.8 kilojoules. If I have twice as much, the amount of energy that's given off is going to be twice as much. And so I can multiply the enthalpy of that reaction by 2 if I multiply all of the stoichiometric coefficients in the reaction by 2. And so we have sort of a first step that actually is 2 sulfurs plus 2 O2 reacting to form 2 SO2. In the second step, there's a couple ways to look at this, but you'll notice that both of the equations, reaction 1 and reaction 2, have oxygen gas in them. That's not always helpful for trying to figure out the overall equation and how these 2 steps occur in tandem. But what you do know is that there's a stoichiometric coefficient of 2 in front of the sulfur trioxide. And so if you go to reaction 2, you'll see it has a stoichiometric coefficient of 2 in front of the sulfur trioxide. So that's good. That means that our reaction, first off, has sulfur trioxide in the products, which is where we want it, and it has the correct stoichiometric coefficient. So we can just take that chemical reaction as is, which means we can take its enthalpy change as is. Now, if we add those 2 chemical reactions together, right? So we just take all of the reactants. So the reactants from the first equation, so sulfur, so 2 sulfur plus 2 oxygen, right? Those react to form, so 2 sulfur plus 2 oxygen, and we take the reactants from the second equation, 2 sulfur dioxide plus oxygen, and then we put our arrow in the middle, right? And then we take our products, we get 2 sulfur dioxides as a product from the first reaction, plus 2 sulfur trioxides as the product from the second reaction, and that's the sum of these 2 reactions, right? So we're keeping everything on one side of the reaction arrow, on the reactant side, everything on the product side as we combine these 2 reactions. But what you'll notice is the 2 sulfur dioxides, those are the same, right, on either side of the reaction arrow. So it's not a spectator ion, but it's similar to those spectator ions that we can get rid of them. We can cancel those out. It's sort of like adding or subtracting the same thing to either side of an equation, right? So in this case, if we subtract 2 SO2 from both sides of the equation, we get rid of them. And if we do that, and if we did our preparation right, we could wind up with that original equation that we started with that we're trying to get up here. And if we do that and we did it right, that being the same as the overall reaction above, we can now say, well, how did we get that? Well, we added, right? We added the 2 enthalpies seen here, right? So you take now and say, okay, well, our overall reaction has an enthalpy change that's 2 times the first reaction 1's enthalpy change plus 1 time reaction 2's enthalpy change. So you add them together and you wind up with the enthalpy change for this overall reaction. And so what Hess's law tells us is that the overall enthalpy change for a given reaction that takes place in multiple steps, that enthalpy change for the overall reaction can be calculated by adding the enthalpy changes from each individual step, okay? Assuming you can get the overall reaction by the calculation that we just did, okay? So that's what's going on with Hess's law. You can basically add up the enthalpy changes of all the steps to get the overall enthalpy change of a chemical reaction. Okay? So there were some strategies in there, but before we get to doing another example of this, I want to talk us through some of the processes. Actually, if we go back to this, you'll notice in the first part of this, right? In that first part, over here, right? When we had that first part there, right, I multiplied that reaction by 2, and I had to multiply the enthalpy change to get that, the enthalpy change of the reaction by 2 as well, right? So when I said reaction there, when I did that, it was times 2. And if I take this, bring it down there, that's also got to be times 2, which says that if we manipulate these equations, we need to be able to figure out what do we have to do to the enthalpy in order to get them to work properly. Okay? And so that brings us to some rules for working with enthalpies of reactions. First one, if you just have some chemical equation, okay? And so our chemical equation is just generic. A plus 2B reacts to form C. Whatever the enthalpy change is associated with that, okay? X kilojoules, okay? We're going to use that as our baseline. So if you take and double those stoichiometric coefficients, so you go to double every single one of them, because you have to do that to keep it balanced if you're going to double the equation. So we're left with this delta H prime. Okay, and the prime is just saying it's different from the original one. That's all that's there to do. And so if you double the overall stoichiometric coefficients, the enthalpy change is doubled. If you were to have the stoichiometric coefficients, right? So, that's not right. I've got an error in my notes here. Oh no, that's right. So now on this one, I'm going from there. So I'm comparing the wrong equations with my eyes right now. So if you have the stoichiometric coefficients, right? So you go from A to A over 2, or 1/2 A, and from 2B to B, and from C to 1/2 C, then you take and you multiply that stoichiometric coefficient, or the enthalpy of the reaction, by the same value that you multiplied the stoichiometric coefficients. So if you have the stoichiometric coefficients, you have to have the enthalpy change as well. Okay. The other one that we talked about here is if you just cause the reaction to be reversed, right, it causes the sign change, right, to the enthalpy of that reaction. Now, in doing these types of problems and figuring out the overall enthalpy change or heat associated with a reaction, you might have to do more than one of these at the same time. But these are the basic rules for it, right? If you multiply all of the stoichiometric coefficients by a value, you have to multiply the enthalpy change of that reaction by a value. If you reverse the reaction, right? When you reverse the reaction, you multiply the enthalpy change by -1. You basically change the sign of the enthalpy change when it's reversed, okay? So those are the basic rules that we can use when we work with these enthalpy changes of reactions. Okay, so here we've got an example. So another example of gas chemistry, of chemical reactions that occur in the gas phase that, could potentially, be things that are happening around us, although less often in LA right now because we're not producing as much carbon monoxide because there are fewer cars driving. But here's our example. We've got 2 pollutants that form an auto exhaust. Right? So carbon monoxide and nitrogen monoxide. An environmental chemist must convert these pollutants to less harmful gases. So CO and NO are bad. They bind to things like hemoglobin. They react in very bad ways. So you want to convert them to things that are less harmful. Carbon dioxide, less harmful than carbon monoxide. And nitrogen gas. Nitrogen gas, not harmful at all, right? That's the majority of the atmosphere. And so that overall reaction occurs via two possible types of reactions. The first one, equation A, says carbon monoxide plus 1/2 O2 reacts to form CO2, right? And so that's associated with a delta H of reaction of 283.0 kilojoules, exothermic. And the other potential reaction is nitrogen plus oxygen go to form 2NO. Now you might get these two sets of data from, say, a table, right? A table of enthalpy changes for chemical reactions. So, or they might be experimentally determined things that have been determined in a laboratory. So what we can now do with these reactions, we can use equation A and equation B to help us to figure out the enthalpy change of the overall equation up here. So we want to find the delta H for this equation, right? So delta H, we'll call that delta H of reaction, okay? And that RXN is just saying reaction. Okay, so how do we do that? Well, this is where we can compare our reactants to the equations that were given, right? So if we have carbon monoxide, we want one of these two equations to have carbon monoxide in the reactants as well. And you can see equation A has carbon monoxide. That carbon monoxide in equation A has the same stoichiometric coefficient, so that's a good place to start. So we can just take, assuming we have these two reactions to work with, we want directly equation A, okay? We don't want to do anything to it. It's fine the way it is because this carbon monoxide in that equation has the same stoichiometric coefficient as the carbon monoxide up here in the overall equation that we're looking for. So CO, gas, plus 1/2 O2, gas, react to form CO2, gas. And so this delta H, right, is going to be the same. And here I'm going to label, by the way, I'm going to go up to my delta H's up here. So delta HA and delta HB. So the delta H for this reaction is the same as delta HA, which will equal negative 283.0 kilojoules. Okay. So our first reactant is taken care of. Check if we did it right. Our second reactant that we need to deal with is nitrogen monoxide. Well, if I look at the other or both of these equations, I don't have nitrogen monoxide anywhere except for on the product side of this chemical reaction, of the second one, equation B. So in order to get this to work right, I need to take the reverse of equation B. But I need to also notice that the stoichiometric coefficient here in equation B is a 2, whereas the stoichiometric coefficient in the overall reaction is a 1. And since that's the case, I don't just need to reverse it, I need to take 1/2 of equation B also. So I'm reversing it and taking half of all of the stoichiometric coefficients, okay? So when I do that, now I have a reaction. Well, I take half of NO, or excuse me, half of 2NO, which is NO gas, so nitrogen monoxide gas, react to form. Here it would be 1/2 N2, because remember I'm flipping it and taking half, 1/2 N2 gas plus 1/2 O2 gas. Okay, so when I now have this particular reaction, I've got negative, because I've reversed the reaction, 1/2 of the delta HB is really the delta H for this particular reaction. And so for that, I should just get negative 90.6 kilojoules. Okay. Now, if I've done this right and I've set this up properly, and when I add these reactants,
90.3.
so CO gas plus 1/2 O2 gas, right? So there's the reactants from the first equation plus the reactant from the second equation. So NO gas, those react to form, well, the product from the first equation, CO2, plus the product from the second equation, 1/2 N2 gas, plus 1/2 O2 gas. Oh, there we go. Okay, if I look at those, now I can see, well, the 1/2 O2 and 1/2 O2 are the same on either side, so I can get rid of them. And I can rewrite the overall equation just to make sure it's the same as what I had above that I was trying to get. So CO gas plus nitrogen monoxide gas react to form carbon dioxide plus 1/2 nitrogen gas. Yeah, that looks pretty good, right? If I go back up to that, right, CO plus NO goes to form CO2 plus 1/2 N2. That looks good. And so what do I do now? I just add those two values together. So I get a delta H equal to, Amir, one moment. Should be 373.3. Oh, that should be a 0.3 here. Yeah. So negative 373.3 kilojoules. Yeah, Amir.
You fixed it, thank you.
Okay. Okay. And so that's how Hess's law works, right? You may have to do some manipulations, right? Those manipulations are sort of like you see here, right? This reverse or 1/2 or multiply by 2. But if you do that, you can figure out the overall chemical reaction, the energy associated with that chemical reaction, okay? So let's think about this now, just briefly from, if we go back up to our sort of a picture of our chemical reaction here, okay? So here's our coffee cup calorimeter, okay? In this coffee cup calorimeter, if I just have a chemical reaction that takes place in there, remember I'm measuring the temperature of the water, right? So if that chemical reaction is exothermic, the temperature of the water will go up because the water is absorbing the energy from the chemical reaction. If the chemical reaction is endothermic, the temperature of the water will go down, right? And so that's how you would measure the enthalpy change of a reaction. And so if you were to measure the enthalpy change of a reaction doing calorimetry, you can think about it from the standpoint of the following. I'm gonna throw in, here we go. So you can think about it from the standpoint of the following. If you have the enthalpy change of a reaction, okay? So some chemical reaction, that right there, plus the heat absorbed by, say, the water in the calorimeter, right? Right? If you add those two things together, that will be 0, right? And so what that means is if you have the enthalpy of reaction that is exothermic, then in order for this to be to equal 0, the energy of, or the heat of that's absorbed by the water will be positive, right? And so that's how you would do something with a chemical reaction. So you could say that delta H of reaction will equal negative Q of the water, right, in that chemical reaction, okay? And so you could measure it just based on how much water you have, right? Q, excuse me, that's not what I'm, try this again. Come on, there we go. Where Q is equal to the mass of the water times the specific heat of the water times the change in temperature of the water. Okay. Well, when we think about this delta H here, right, that is for a reaction as given. Or as written. You can also figure out the heat per mole, right? So you could say the delta H of a reaction per mole of reactant right? Per mole of a reactant would just be the Q, or negative Q, I should say, that's associated here per number of moles of reactant. Okay, and so you could actually figure out how much energy is given off when an acid reacts with a base, how much is given off per mole of acid or per mole of base. And just by dividing by that value that you get experimentally, dividing that by the number of moles that react. Okay. All right, and so that's how Hess's law would work. All right. So now we've gone through that. The last part of this chapter is using standard enthalpies of formation. Okay, so a standard enthalpy of formation can be used to calculate the energy of a reaction. And essentially what standard enthalpies of formation are, or they're going to do, is you're going to use them like you use Hess's law, or using Hess's law to figure out the enthalpy of a reaction. But first we have to understand what the standard enthalpy of a formation is, okay? So the standard enthalpy of formation, it's a chemical reaction, and it's a chemical reaction that is listed in a table. So we're going to see a table here in a second, so we'll come back to this table. But basically it's a chemical reaction that occurs under a standard set of conditions. So for us, the standard conditions, well, we like to compare chemical reactions that take place under a standard set of conditions. So we're comparing all the things that are the same, except for maybe the chemical reaction of one that occurs in one case versus a chemical reaction in another place. So we want to keep things that we can control the same. The standard conditions that we tend to use for chemical reactions are 25 degrees Celsius, 1 atmosphere, and 1 molar. So this is different than STP for gases. For gases, STP is 0 degrees Celsius, but for standard conditions for chemical reactions, especially ones that take place in aqueous solutions, it has to be 25, because 0 degrees Celsius, you start running into problems with potentially freezing the water. And so when we say these standard conditions, we're just comparing reactions that take place under these standard sets of conditions, okay? You just need to know that for a gas, the standard temperature is 0 degrees Celsius. For reactions, it's going to be 25 because we're avoiding freezing, okay? And so when we think about the phase of a pure substance, this is going to be sort of important to think about in a minute, whether we're talking about an element or a compound, whatever that pure substance is, it's the stable state, right, under standard temperature, in this case 25 degrees, or whatever standard that table uses, right, or whatever standard they took the data, whatever standard temperatures and pressures they took the data at, right? So at 25 degrees Celsius, which, by the way, if you remember the big old periodic table in our lecture hall, it had the different colors for the different elements, and we said, you know, most of the elements are solid at room temperature and 1 atmosphere of pressure, right? Those were the black elements. And then we had the blue elements were liquids. So there were only 2 elements that are liquids at standard 25 degrees Celsius and room pressure, right? Those were mercury and bromine. And then you had the other ones that were, so those were blue. Then you had the red elements, which were the gases. So hydrogen, oxygen, etc. Those are elements, right? We know something about certain compounds. Carbon dioxide, okay? At standard temperature and pressure, it's a gas, right? So that's what we're talking about with the phase of these substances, okay? Now, that being said, what is a standard enthalpy of formation, okay? So the standard enthalpy of formation is the following. Okay, and actually I need to add a slide in here. Okay, so 1 second. Let's see. We're going to add a slide into this in a second so I can really define this more. Okay. Back to our screen. So a standard enthalpy of formation. It's basically this. Okay, it is the enthalpy change associated with the formation of a compound from its elements in their standard state. Okay, for example, if we were to take and make carbon dioxide, the formation of CO2 gas from its elements, right? Well, I've got carbon. So carbon in its most stable state is carbon solid. It's graphite. Okay, plus oxygen gas. Okay, that's that is the equation, the chemical equation for the formation of carbon dioxide. Okay, we have a compound and it's formed from its elements in their most stable state and it's balanced. Okay, but notice it's 1 mole of carbon dioxide. And so this will have a delta H naught of formation. Okay, that right there, right, before we actually go and look at the table and find it, right, that has 2 things to it that we need to make sure we're clear on. That little circle there, that knot, okay? Okay, that is just specifying that says it's under standard conditions. Okay, now that formation, that's right, that's something where that essentially says that if you have carbon dioxide, the delta H naught of formation for carbon dioxide, right, is making carbon dioxide from these 2 reactants, right? Those specific reactants are the elements in their standard state, okay? And so you would find that. You'd really just go find that in a table. And so the table that we can look at is a table like here, and we'll come back to this in a second. So if you look for carbon dioxide, right? So we're gonna go over to our table. Notice carbon dioxide is right here. Okay. So there's carbon dioxide for us. So that has a standard enthalpy of formation of negative 393.5 kilojoules per mole of carbon dioxide. Okay, and that's where you'd find that value in the table. Now, if you were looking at the standard enthalpy of formation for an element, well, for example, if I wanted to know the standard enthalpy of formation of N2, right? Well, so N2 gas. Well, remember, if whatever that substance is, I'm talking about making it from it's reactants that are the components of that substance in their standard state. Well, nitrogen in its standard state is just N2. So the enthalpy of formation of that nitrogen gas, or for any element, is going to be 0. So this is another one of those times where it's important that you know those homonuclear diatomic elements, is because this is where it might come in, right? The standard enthalpy of formation of, say, oxygen gas, right, is going to equal 0. Okay, so when it's a compound, it's the compound coming from its elements. If it's an element in its standard state, it's already in its standard state, so its standard enthalpy of formation is 0. Yes, Maya.
Hi, so the chart you were referring to isn't in the chapter 6. It looks like it's from a different chapter.
There
Are
is,
you just gonna
there is an
provide that for us?
appendix. It's, yeah, so you would get the values, or I would give you a chart. Okay.
Oh, okay.
Yeah, so there, it's appendix. Do I have it in here? Hold on. I didn't list it in here. Give me a second. I can tell you which appendix it is in your text here. Just a second. I forget which one this is. Here we go. So in your textbook, appendix 4 has selected thermodynamic data, and the standard enthalpies of formation in that table, in appendix 4, the standard enthalpy of formation data is the first column of that table. Don't worry about the second or third columns in that table, because the second and third columns are things that you won't explore until you get into thermodynamics in Chem 102. Okay. And so what we'll do here is we're gonna pick up on this slide when we come back tomorrow, and we're gonna use the standard enthalpies of formation to calculate the enthalpy change for a given reaction. And we're essentially using Hess's law to do so, but in a simpler way. Okay, so Amir?
My question was on the slide that you were doing just before this one. You said for an element, well, for the diatomic ones, I can totally understand. How about for the ones that are not diatomic, saying for carbon? If we used to have a carbon and became two carbon, first of all, is that even possible? And second, if it is, how can we?
So it's in its most stable state. So for carbon, it's carbon solid, because carbon in its most stable state as an element is a solid, and it's graphite. Okay, so for that, that's going to be 0 kilojoules per mole. Okay, if, however, you have carbon that's not in its most stable state, so carbon solid, say for diamond. Okay, carbon for diamond, you can go to this table here, and you can see that carbon for diamond is going to have a value. It's a very small value, so 1.897 kilojoules per mole. And so here you go 1.897 kilojoules per mole. Right, so this is where graphite is a little bit more stable than diamond, right? Which is why, you know, graphite lasts forever and not diamonds, right? But it's specifically in the most stable state. So yeah.
So does it mean basically carbon needs that much energy for it to? No, it doesn't.
That is, if you were to change graphite into diamond, the overall enthalpy change from graphite to diamond is, the diamond is a little bit higher in energy. It's a little less stable. Now the getting there, that's different. That's a different story that's governed more by the rates of the reactions and what's called an activation energy, which is a very different thing. So just looking at where it's at, right? Graphite more stable than diamond. Getting graphite to diamond, not an easy thing to do. Getting diamond to graphite, also not an easy thing to do, right? So there's a difference in how to get from one to the other directly.
Basically, if we get from one to the other, regardless of how we do it, that would be the amount of energy as endothermic energy they would give us.
That's right. Yeah.
And one more question, is the carbon plus oxygen on the top part that you wrote, that's not a combustion reaction, is it?
Yeah, you can burn graphite with oxygen, yes. So think of coal, charcoal, right? It's the same idea.
Because we didn't have water in this reaction, that's what I'm asking.
Right, so remember, a combustion reaction is the reaction of something with oxygen to produce an oxide, basically. In terms of a hydrocarbon will produce carbon dioxide and water. But you can have combustion of a metal. For example, magnesium reacts with oxygen to form magnesium oxide. That's still a combustion reaction, but in that case, you don't have either carbon dioxide or water produced.
Thank you.
Professor, one last question about tomorrow's quiz. It's up until 6.2, you said? Until
yeah, it's through
today's lecture?
Yes, through the stuff that we did. So the end of chapter 5 stuff that wasn't on the last quiz through the beginning of chapter 6.
You say beginning, that's up to 6.1 or just 6.2?
Hold on one sec. Let me just stop the recording here.